In this lesson, we'll introduce the implicit differentiation. First of all, let's make sure that we understand what that means, the implicit. So far, the functions that we have seen are mostly expressed explicitly as the function of x. And here are a couple examples, like y equals x times sine x. It's very explicit. What is y? X times sine x. And then here, this is another example, y equals square root of x squared plus 1. Now, sometimes functions are defined implicitly between x and y. For instance, like here, x times y is 1. You don't see the function y explicitly like what we just saw earlier. It's defined as an equation. So to find the derivative of y, now we can definitely, first of all, write this equation explicitly so that y is a function of x. Like for instance, you can divide both sides by x so that y is equal to 1 over x. And then you differentiate it. So this is the implicit form because it's not very clear what the y is. And then this is the explicit form. It clearly shows you what y is. And then to find the derivative, you differentiate using the existing differentiation rules. Now you might feel like, okay, now if you have a function that's not defined explicitly, then we can always solve for y and then just differentiate from there. So just like how you would do it here. However, it is not always easy to solve for y by hand for some equations. Just name one example, like this one, x cubed plus y cubed equals 6 times xy. So, by the way, this is the graph of this guy is called the folium of Descartes. It is actually difficult to solve for y. Even after solving for y, it is more difficult to find its derivative because it is oftentimes pretty complicated looking. Fortunately, we have a method of implicit differentiation. It allows us to find the derivative of y without first solving for y. To find this dy dx implicitly, note that the differentiation is taking place with respect to x. What that means is when differentiating terms involving x alone, we differentiate as usual. However, when differentiating terms involving y, we have to treat this y as a function of x, and the chain rule must be applied. Let's look at the following examples. In the first example, we need to differentiate this function x cubed with respect to x. Now you see that this variable and this variable, they are the same variable, right? So here variables agree. And when they agree, you just use the regular power rule here. So we are going to differentiate 3x squared using the power rule. Next example, we want to differentiate y cubed with respect to x. Here, this variable is y and this variable is x. They do not agree. So here, variables disagree. In this case, you will have to use chain rule. You should think of this y as a function of x. So basically, you should think of this as, okay, the y is a function of x. So you want to differentiate some function raised to power 3, and this function is a function, the inner function is the y. Now, then you have to use the chain rule. So basically, we do know that when we have u to the n, when we differentiate that, we use the general power rule, right? n times u to the n minus 1 times the derivative of u. So in this case, this u in our example is going to be the y. That is going to be the y prime, right? And this will be the y to the n minus 1. So with that, we are going to say 3 times what square? The y square. And then times the derivative of this inner function. So think of this as a function of x. So the derivative of y will be just dy dx. And oftentimes I prefer to write it as 3y squared times y prime because it's a little less complicated looking, but they represent the same thing, a little easier to write. Okay, with that, let's move on to the next example. Here we have sum of or difference of several functions. So the derivative of the first one, which is x, the variables agree, so we just use the regular power rule. So it's going to be derivative of x is 1 minus, so the derivative of y squared now, this variable is y, this is x, so they do not agree. We have to use chain rule. And again, just use this general power rule. We have 2 times y to the power 1 times the derivative of the inner function derivative of y. So again, I usually prefer to write y prime. You can write dy dx. And then plus the derivative of y with respect to x. Again, this is not x, right? So we cannot just write 1. We are going to say the derivative of y with respect to x is dy dx, or just y prime. Okay, so therefore this is the result of the this is the derivative of this function. Next, we have a product of two functions. One is x, the other one is sine y. So we need to use the product rule here, right? Now the product rule says the derivative of the first function times the second function plus the first function times the derivative of the second function. And derivative of x, just the regular differentiation, so it's 1. So I'm going to skip writing the 1 times sine y. Again, this is the derivative is just 1. This is equal to 1. And here plus x times the derivative of this, we have to use chain rule, where the inner function is the y, the outer function is sine of the u, right? The inner function u is equal to y. The derivative of sine is cosine, so cosine of y times the derivative of y, which is y prime. So this is the derivative of this product. Again, the trick is always think of y as a function of x. When you find the derivative of that, when the variable do not agree, use the chain rule. All right, let's look at more examples. And first of all, let's introduce the suggestion, the general suggested steps for implicit differentiation. First of all, you differentiate both sides of the equation with respect to x. Again, treat y as a function of x. So keep in mind, y is a function of x. And step 2, you just solve the resulting equation after you differentiate both sides with respect to x. Solve the resulting equation for dy dx, which is the y prime. Then you get the derivative of the y. Let's look at this example here. Consider this equation, x squared plus y squared equals 1. By the way, this actually is a unit circle, right? Unit circle. And let's find the dy dx using implicit differentiation. You may wonder, okay, I actually can solve for y and then take the derivative using the explicit form. Well, let's practice on using the implicit differentiation. You definitely can do that, but let's stick with the implicit differentiation here. And later on, you'll see sometimes it's just impossible for you to solve for y, and you will have to use implicit differentiation. All right, step 1, we're going to differentiate both sides with respect to x. So in other words, we're going to differentiate the left side and the right side with respect to x. The left side, the first term is x squared. The variables agree, so we just use the regular differentiation rule. We have 2x. The second term, it is y squared. Now the variable is x, here the variable is y. They do not agree. We have to use the chain rule. And then we will have 2y times the derivative of the y, right, which is y prime. The right-hand side, 1 is just a constant, so derivative of constant is equal to 0. So we've done the first step. The second step is just to solve for y prime, and we are going to isolate this variable term. So 2y prime equals negative 2x. Subtract 2x to both sides. And then finally, y prime is equal to negative 2x over 2y. And cancel the 2. We have negative x over y. And very often, when you use implicit differentiation, the derivative oftentimes is a function of both x and y. So it sometimes, very often, involves both variables. Now let's look at the second part. Find the equation of the tangent line to the curve at this point, 1/2 and negative root 3 over 2. Again, just want to visualize what's going on. The original equation is a unit circle equation, so this is a unit circle. And what we are looking at is when x is 1/2, y is negative root 3 over 2. So when x is 1/2 and y is root 3 over 2, which is somewhere here, we want to find the equation of this tangent line, right? So that's what we are trying to find. We need the slope. We already have the point. So the slope is equal to the y prime. You will have to plug in the points. The x value is 1/2. The y value is negative root 3 over 2. And this is the derivative. Let's plug in x and y here. X is 1/2. Y is negative square root of 3 over 2. And when you simplify this, negative becomes positive. It is equal to 1/2 times 2 over square root of 3, which is 1 over square root of 3, which is square root of 3 over 3. And just use your common sense to check, and we can see that at this point, the slope is actually supposed to be positive, and we actually have a positive slope. So that seems to be good, right? Now, after that, let's find the equation of the tangent line using the point slope form. So y minus y1 equals the slope times x minus x1. And let's simplify from there. So y plus root 3 over 2 equals root 3 over 3x minus root 3 over 6. And finally, we subtract root 3 over 2 to both sides. So therefore we have y equals root 3 over 3 x minus root 3 over 6 minus the root 3 over 2. And definitely we want to get a common denominator, right? So that these two constants can be combined. So we have root 3 over 3x minus, and here we have negative root 3, and here we have negative 3 root 3. So we have a total of negative 4 root 3 over 6. And we definitely can cancel the 2. And finally, this is root 3 over 3x minus 2 root 3 over 3. Now, let's move on to the next part. So here, we want to introduce a new term. Find the equation of the normal line. A normal line is a line that is perpendicular to the tangent line. It is actually one of the important concepts in a later calculus class. So we want to find the equation of this normal line to the curve at the same point. So earlier we found the tangent line. And what is normal line? I'm going to show you here on this graph. The normal line is actually perpendicular to this tangent line, okay? And this is the normal line. Earlier one, that's the tangent line. To find, we need the slope. So here the slope of the normal line is equal to, because it's perpendicular to the tangent line, it should be negative 1 over the slope of the tangent. And we already know the slope of the tangent, which is actually, we found it earlier, 1 over square root of 3, right? So therefore 1 over the square root of 3, which is negative square root of 3. And it actually matches what we see here, the slope is negative. And therefore, the equation of this normal line will be y minus negative root 3 over 2 equals negative square root of 3 times x minus 1/2. Then we have y plus root 3 over 2 equals negative square root of 3x plus root 3 over 2. And you can see that actually when you subtract root 3 over 2, these two cancel. Therefore, we have y equals negative root 3 times x. And this line actually passing through the origin. Okay. All right, so we've seen one example of using the implicit differentiation and to find the equation of tangent line and normal line. Let's do some more examples and practice the implicit differentiation. Implicit differentiation is pretty useful in deriving some other more formulas. For instance, let's try to find the derivative of y for this function sine y equals x. And when we have sine y equals x, this actually is equivalent to y equals sine inverse of x, right? So when we find the derivative of y, we actually derive we are deriving the derivative formula for the inverse of sine x, which will be learned in the future. Here we are going to say, let's differentiate both sides. Derivative of the left side will be cosine y. And again, you cannot stop here because when we find the derivative with respect to x, the variable do not agree. So we have to use chain rule. So we have to multiply by the derivative of y, which is y prime. And the right-hand side derivative of x is just 1. So therefore, y prime is equal to 1 over cosine y. And maybe at this moment we are satisfied here. So this could be the acceptable answer. Now, actually, we can do a little better. In the future, we actually want to write this in terms of x. So keep in mind, this is what is y? Y is sine inverse of x, right? So therefore, this is 1 over cosine sine inverse of x. In your trigonometry class, usually you have this kind of exercise to have you simplify this kind of expression. When you have this kind of expression, you want to draw a right triangle. So I'm going to draw a generic right triangle. And here, y is sine inverse of x, which means sine y is equal to x, right? And you should treat this y as a angle. So which means I'm going to just call this as y, okay? And sine, this is saying sine of y is equal to x. And sine of y is, so in this case, sine of y is equal to opposite over adjacent, right? You want this result to be equal to x. That means here you assign this as x, this as 1. So you call this as x, this is 1. So this graph perfectly matches this expression or this expression, they're equivalent. So I created this graph based on what I see here. Now, so therefore, what is our answer here? Cosine y, right? This angle is y. Cosine y should be adjacent over the hypotenuse. And what is adjacent? Using the Pythagorean theorem, this adjacent should be 1 minus x squared. So 1 squared minus the x squared, which is 1 minus x squared, and then take the square root for this side. So therefore, using this figure, the cosine y is actually the adjacent over the hypotenuse, square root of 1 minus x squared over 1, which is square root of 1 minus x squared. So therefore, this guy is actually 1 over cosine y is square root of 1 minus x squared. We can actually derive this using trigonometric identity from this step, but we alternatively we can use this triangle to derive this directly from here. So now you can see that y prime is actually equal to this guy. And what is y? Y is sine inverse of x. So in other words, what's the derivative of sine inverse of x? It will be 1 over square root of 1 minus x squared. Again, this will be studied in the future. So for now, you don't really have to memorize this one. It's just to show you how powerful implicit differentiation is, and it can be used to derive a lot of new formulas. Next, let's take a look at this example. We have left side, we have a sine of xy, the right side, x squared plus y. Let's differentiate the left side with respect to x. So because this is sine of some function, so we should use chain rule, right? So using the chain rule, the derivative of left side will be cosine of this inner function times the derivative of the inner function. So I'll do another step to find the derivative of this product. The right-hand side derivative of x squared with respect to x will be 2x plus the derivative of y, which is the y prime, right? or just say dy dx. I prefer to write y prime actually. Now let's continue to find the derivative of this product. Now we have to use product rule. Derivative of x is equal to 1 times y plus x times the derivative of y, which is y prime. So I'm going to actually, let me write y prime instead of dy dx. A little easier. So the right hand side is 2x plus, let's change this to y prime. Okay. Next, we need to solve for y prime. In order for you to solve y prime, we have to group the terms with y prime together. So I'm going to distribute this. So the first term will be cosine xy times the y, which means y times cosine xy, plus xy prime times cosine xy equals 2x plus y prime. And we need to group the terms with y prime together. So we have xy prime cosine xy minus y prime. So we subtract y prime to both sides. Of course, we still have this term here. And the right hand side, we still have 2x, right? So basically, subtract y prime to both sides. And now we have to move this term that without the y prime to the other side. So we have, and at the same time, we should factor out the y prime after we move that over. So the right hand side, we should have 2x minus y times cosine xy. So here we subtract the y cosine xy to both sides. And the left hand side, we are left with y prime. I'm factoring out the y prime. So we're left with x cosine xy minus 1. And now finally, we need to solve for y prime, right? So we divide both sides by this factor. So therefore, y prime is equal to 2x minus y cosine xy divided by x cosine xy minus 1. Well, it looks a little complicated. However, just think about it. Here, you really cannot solve for y, and you cannot use the traditional method to find the derivative of y, versus we have this approach to solve for the y prime. Okay, let's take a look at another example. Earlier we introduced this x cubed plus y cubed equals 6xy. This is the volume of Descartes. This graph, if you use Desmos to graph this equation, just type in this equation in Desmos, and this graph looks like it's a beautiful graph. It's something like this. It's symmetrical actually, because you can see this graph. It's kind of symmetrical if you replace x with y and y with x, it's still the same thing, right? So it's symmetrical graph. And 3 and 3 is actually located at this tip. This is 3 and 3. And let's find the derivative of this equation with respect to x for the y. And then we want to find the tangent to the curve at this point, which means we want to actually find the equation of this guy, this line. To find the derivative, let's differentiate both sides with respect to x. So here we have 3x squared plus, when you differentiate this guy, it's not, we need to use chain rule. It's 3y squared times the derivative of the y, which is y prime. And the derivative of this guy, we need to use the product rule. Derivative of 6x is equal to 6 times the second function y plus 6x times the derivative of the second function, derivative of y is y prime. Now let's group the y prime terms together, and we have 3x squared plus 3y squared y prime minus 6x y prime equals 6y. And then we need to subtract both sides, 3x squared, so that only y prime terms are left on one side. So we have 3y squared, and at the same time, I'm going to factor out the y prime equals 6y minus 3x squared. Again, factor out the y prime here from these two terms. And finally, y prime is equal to 6y minus 3x squared over 3y squared minus 6. And you can see we actually can divide, there's a factor of 3 here, we can divide 3. We have 2y minus x squared, y squared minus 2x. Now we've got the derivative of the y, so we should be able to find the slope at this point and then find the tangent. So the slope is going to be the y prime, evaluates at 3 and 3. Let's plug in the 3 into here. So we have 2 times 3 minus 3 squared, and then 3 squared minus 2 times 3. And you can see that they are the same thing, just switch the position. So therefore, this is -1. And finally, the equation will be y minus 3 equals -1 x minus 3. So therefore, y minus 3 equals -x plus 3. And the equation is y equals -x plus 6. And it should make sense, right? It matches what we see here. To close this section, we're going to take a look at a couple examples that involve second derivative. Earlier, we found the first derivative for this equation. This represents a unit circle. And let's quickly redo the first derivative. So let's differentiate the left side. The first term, the derivative of x squared is 2x. And the derivative of y squared, again, we take the derivative with respect to x. The variables do not agree, so we have to use chain rule. 2y times derivative of y dy dx, right? Equals derivative of the right-hand side, because it's constant, it's 0. And we solve for y prime, so we have 2y y prime equals -2x, or y prime equals -x over y, where the 2 is cancelled. Now, to find the second derivative, there are actually a couple different ways. One way to do that is we just find the derivative with respect to x. Again, right? So the second derivative is the derivative of the first derivative. So therefore, y double prime, which is the derivative of y prime. And to find the derivative of this guy, again, think of y as a function of x. We use quotient rule. Then we have, there's a negative sign. And the quotient rule says in the denominator, it's the square of the low function, y squared. Top, we have low dy, the low function, times the derivative of the low d high, the derivative of the high function, which is derivative of x, and it is 1, minus high d low, right? X is the high function times the derivative of the low function, which is the y. So derivative of y is y prime. And now this is equal to negative y minus x times y prime. What is y prime? We already found it in the earlier step. So therefore we do the plug in y prime, x times negative x over y. And let's simplify. In the numerator, it's y plus x squared over y. The denominator is y squared. Let's multiply the top and bottom by y to clear the fractions, and therefore we have negative. Numerator we have y squared plus. When you multiply this, the y is cancelled. We're left with x squared. And at bottom we have y cubed. And we can actually simplify this a little further. What is y squared plus x squared? We know from the given equation it is equal to 1, right? X squared plus y squared is equal to 1. So therefore our final answer will be 1 over y cubed with a negative sign. Actually, there's another approach. If you look at from earlier here, by the way, we can divide both sides by 2. So this equation, when we take the derivative on both sides, it can be simplified as x plus y prime equals 0 by dividing both sides by 2. So divide by 2, right? And then after that, to find the second derivative, let's differentiate both sides again. So the derivative of the x is going to be 1. So here we are going to differentiate again. That will create second derivative. So derivative of x is 1. Now the derivative of y times y prime, you will have to use product rule. So it will be derivative of y times y prime. So it will be derivative of y is y prime times the second function, which is the y prime, plus the first function, which is y, times the derivative of the second function. So derivative of y prime is y double prime. So y double prime. So here this is coming from the derivative of y prime equals, the right hand side is 0. Because we want to solve for y double prime, so we want to find y double prime, let's solve for that. And here we have y prime square. This is actually the y prime square, right? So here we have 1 plus, and what is y prime square? We already know this y prime. So therefore, let's square this guy. It's negative x over y squared plus y times y double prime equals 0. And let's isolate this, the term with y double prime. We have y double prime equals, and these two terms need to go to the other side. It becomes negative 1 minus, by the way, the square, this square, the negative sign will be gone, right? So it's going to be x squared over y squared. So we need to subtract x squared y squared. And finally, we'll divide by y. Or maybe we can do a little simplification here. Minus, think of this as y squared over y squared. And we have negative y squared plus x squared over y squared, because we also factor out the negative sign, so therefore this becomes positive sign. Okay, finally, y double prime is equal to negative. This y squared plus x squared is equal to 1, and y cubed, right? Because we kind of multiply by 1 over y, multiply by 1 over y. And this is the same as what we just had. So there were a couple different options for you. Choose whatever the way that you prefer. All right, last one. This one should be a little easier than the one that we just did. So strongly encourage you to pause the video and give a try. So first derivative is going to be 1 plus 2y times y prime equals 0. And therefore we have 2y y prime equals negative 1. And y prime is pretty easy to solve. Just simply divide both sides by 2y. And to find the second derivative, I actually prefer to use, instead of quotient rule, I prefer to use power rule. So I'm going to write this as negative 1/2 y to the negative 1, right? And then so that we can use power rule to find this one. Okay, so the second derivative will be the derivative of the first derivative. So it's going to be negative 1/2 times negative y to the, we have to subtract 1 from the power, times chain rule is used, the derivative of the y. And therefore this is equal to, we have negative sign becomes positive. So 1 over 2. And this is y to the negative 2, which means 1 over y square here. Times the y prime. And what is y prime? This is my y prime. So times negative 1 over 2y equals negative 1 over 4y cubed. And if you would like to use the approach that I showed you here for this problem, you can, so alternatively, you can differentiate this, right? Differentiate this again. So let's do a quick one. So when you find, oops, I think I copied this incorrectly. This is supposed to be just y prime, not y double prime. Right there. This is y prime. So let's find the derivative again. Derivative of 1 is 0. Derivative of this will be, we used products rule. So the derivative of 2y will be 2y prime times the second function, which is y prime, plus 2y times the derivative of the second function. It gives us y double prime equals 0. And this is, then we have 2y y double prime equals negative 2y prime square. This gives us 2y prime square. And the 2 is cancelled. So y double prime is actually equal to negative y prime square over the y. And if you plug in y prime, which is this guy, so therefore this is equal to negative, the y prime is negative 1 over 2y, and then square it over y. And it turns out this is going to be 1 over 4y cubed. All right, this concludes this lesson.